Let's think about what it looks like, what a collection of solutions to a linear equation actually looks like. So suppose we have this linear homogeneous equation, and let's suppose that the matrix A is m by n, and so the vector x must be n by 1, and this 0 vector here must be the m by 1 0 vector. So the collection of solutions to this equation, these are possible values for the vector x, and so that means that the collection of solutions is actually contained in Rn, because it's possible values for the vector x, and x is in Rn. So this collection of solutions is a subset of Rn. Let's call this collection of solutions V. So what we're assuming is if little v, if we have some vector that's in this collection V, then the matrix A times V is actually equal to the 0 vector. So this is just me rephrasing the definition of V, right? V is the collection of all solutions. That means if you choose something from capital V, it actually is a solution to this equation. But what sort of properties does this set of vectors V actually have? One interesting thing about this collection of vectors V is, let's take two vectors out of V, so maybe little v and little w. So suppose these are both from the collection capital V. Well, this means, because they're both in capital V, that means that they're both solutions to this homogeneous equation. So a times little v is 0, and a times little w is also 0. But look at what happens if we multiply them together, right? One way that you can combine vectors is by adding them. So let's ask ourselves what happens if we add these two vectors. This resulting vector, the sum, might be in V, but then again it might not. Well, let's check. How could we check if this sum is in V? Well, V is all capital V is all of the vectors that are solutions to this equation, so let's just check if this vector, little v plus little w, satisfies the equation. We'll multiply it by capital A and see what we get. Well, one property of matrix multiplication here is that it distributes over vector addition. So we can distribute, we get capital A times little v plus capital A times little w, but each of these pieces we already know is 0. So this is the 0 vector plus the 0 vector, but of course that's the 0 vector. So little v plus little w is a solution to this equation, and that means that little v plus little w is itself in capital V. So if you take two vectors from V and add them, you stay in V. This is sort of intriguing. This seems unusual. And there's one other vector operation we could actually ask the same question about. Let's suppose that we have a vector little v in capital V, and suppose we choose a scalar, so maybe a scalar little r from the real numbers. Let's ask, is little r times the vector little v in capital V? Well, we can check the same way. We can check to see if r times little v is a solution to that linear equation. So we'll take our vector that's maybe a solution, little r times little v, and multiply it by the matrix A and see what we get. Well, scalar multiplication and matrix multiplication associate and commute, right? So we can, first of all, erase these parentheses, and then we can move the scalar out front like this. Right, so this is associativity and this is commutativity of matrix and scalar multiplication. But then we can put the parentheses back in like this around the a times little v, but a times little v, that has to be 0 because little v is coming from capital V. So little v is a solution to that linear equation, so a times little v is 0. So we have r times the 0 vector, and that's the 0 vector. So as a result, little r times the vector v, sorry, little r isn't a vector, scalar r times little v is in capital V. So capital V has a couple really nice properties. If you pick any two vectors out of it and add them, you stay in capital V. And if you pick any vector out of capital V and any scalar r, and you do scalar multiplication, then you still stay in capital V. Collections of vectors with this property turn out to be one of the most important objects in linear algebra. So let's give this sort of object a name. Capital V is sort of a world of vectors all unto itself, because if you pick two vectors and add them, you stay in here, and if you do scalar multiplication, you stay in here. So it's a space of vectors that is sort of a world all to its own, but it sits inside some larger ambient Euclidean space, Rn. So for that reason, we're going to call this sort of thing, this sort of collection of vectors, a subspace. So a collection of vectors, capital V, in some ambient Euclidean space Rn is called a subspace when the zero vector is in capital V. And for any two vectors in capital V, when you add them, you're still in capital V. And if you take any vector in capital V and any scalar, then the scalar product is also in V. So one quick way to describe this is just by saying that capital V is closed under addition and multiplication. That is, vector addition and scalar multiplication. Closed is supposed to make you think that like all doors of leaving V are closed because you can't get outside of V, so V is closed. So that's the origin of the word closed. Just to get a handle on this definition, let's check that this collection here is a subspace of R3. So we have three things to check, right? We need to check that the zero vector is in there. So is it true that the zero vector is in this collection? Well, this collection of vectors is all vectors that look like this for any choice of A and B. So in particular, if we choose A to be 0 and B to be 0, the resulting vector will be in this subset. So let's call this capital V. So whatever we get from this formula by plugging in A equals 0 and B equals 0, it will be in capital V just by definition. But if we plug in A equals 0 and B equals 0, we get 0, 0, 0. But this is the zero vector. So right, we've checked this first property that the zero vector is in capital V. So next, let's check that if we take two vectors from capital V and add them, we get another vector in capital V. Let's do that up here. So let's choose two vectors from this collection. Well, every vector in this collection looks like it came from this formula. So one vector in this collection is A plus B, B 2A minus B. Another vector in this collection, well, it's just the same formula, but it isn't necessarily the same values for A and B, so we actually have to use different variables, but with the same formula. So that would be, maybe instead of A and B, let's use C and D. So C plus D, D, and 2C minus D. Okay, so now the question is, if we add these, is this in capital V? Well, how can we tell if a vector is in capital V? To know if a vector is in capital V, we have to know if we can write it in this form for some real number A and some real number B. Well, let's add these things together and see what we get. So just doing the vector arithmetic, we get A plus B plus C plus D for the first entry. For the second entry, we get B plus D. And then for the third entry, we get 2A minus B plus 2C minus D. Okay. And now we're supposed to figure out, is it possible to choose two real numbers so that this, our resulting sum, looks like this template here? It's a little hard to see, but for this particular example, notice that B, or this our second scalar, whatever it is, shows up by itself in the second entry. So that this sum, B plus D, must be playing the role of this scalar. So what we should do, since it also shows up in our template here, it shows up in two other places, we should see if we can make B plus D show up in other places. And sure enough, there's a little algebra we can do to make that happen. In the first entry, we could write this as a plus c plus b plus d. So there's b plus d. In the second entry, it's just b plus d. In the third entry, this one's a little harder to see, but this is 2 times a plus c minus b plus d. So you can see we have b plus d here, here, and here. And we have a plus c here and here. So what we've done is we've expressed this sum as some real number in the blue box plus some real number in the red box. Second entry is just the real number in the red box. And the third entry is 2 times the blue one minus the red one. But that's exactly what this template is. So this shows that this sum of vectors really does match the formula for all the vectors in V, and that means that this is in V. So we started with 2 vectors in V, we added them, and we ended up in V. So that means V is closed under addition. Good, that's the second property for a subspace. Now let's check to see if it's closed under multiplication. So we have to play the same game. Let's take c plus d and 2c minus d. So that's some vector in capital V. Let's multiply it by a scalar. This would give us r times c plus d, r times d, and r times 2c minus d. We want to know, is that in capital V? But again, we can do a little algebra with the entries here. This gives us rc plus rd, and 2 times rc minus rd. And once again, you see we have this vector in the red box, or this scalar in the red box, and this scalar in the blue box. Oh, I've got my reds and blues backwards. I'd better keep them straight. We've got RC is now playing the role of the blue box, and RD is now playing the role of the red box. Right? You see it follows this pattern. So that means that this scalar product is indeed in V, and that means V is closed under scalar multiplication. So this verifies that this collection of vectors has these 3 properties, and so this collection of vectors is a subspace of R3. All right, so that's what it looks like to be a subspace, but what does it look like to not be a subspace? Well, let's look at an example. Here's a collection of vectors. This is in R2. Let's check that it's not a subspace. It's not really obvious at first which of those 3 properties of a subspace we should try to falsify first, but let's just grab a couple vectors out of this collection and add them together and see if we're still in this collection. So let's see. We could get one vector in this collection by choosing, let's see, how about a equals 0? That would give us the vector 1 minus 3. And then if we chose a equals 1, that would give us the vector, looks like 0, 1. So let's add these together and see if we're still in this collection. So let's call this W. So when we add these together, we get 1 minus 2. Is this in W? Well, let's check. If it is in W, then we can write it using the formula that defines W, 1 minus A and minus 3 plus 2A. So we should be able to find an A that makes this true, but look, this is a linear system. We're saying that 1 has to be 1 minus A, and minus 2 has to be minus 3 plus 2A. This first equation, we can solve this for A. This says that A has to be 0, But in the second equation, right, a equals 0 doesn't work for this second equation. Right? If you put in a equals 0 into this template, what you get is 1 minus 3. You don't get 1 minus 2. So this vector, this 1 minus 2, it was a sum of two things in W, but it is not itself in W. And that means that W is not a subspace, because it's not closed under addition. In fact, it doesn't contain the 0 vector either. So, in terms of properties of a subspace, this is how we can check if a collection of vectors is a subspace. But geometrically speaking, what is a subspace? Well, first of all, any subspace has to contain the origin. So let's think about just the plane, the xy plane. What would so this is really R2. What would a subspace look like in R2? Well, for one thing, it has to contain the origin, right? It has to contain the 0 vector. If it contains any other vector, well, then it has to contain any scalar multiple of this vector, so it has to contain the whole line. And so if there's a non-zero vector in a subspace, then it has to contain the whole line. The subspace has to contain the whole line parallel to that vector. The line through the origin parallel to that vector. Okay, what if the subspace also contained a second vector? Well, then it also has to contain the line through the origin parallel to the second vector, but also it has to contain all the sums of vectors that point along these two lines. So it would have to, contain this, because that's the sum of those two vectors, and it would have to contain this, because that's the sum of this vector and this vector, and so on. Much like with span, we could actually cover the whole plane by taking sums of vectors along these two lines. So when you visualize a subspace, what you should imagine, it seems, is some sort of span of vectors sitting inside of a larger ambient space. So geometrically, the reason why this collection isn't a subspace, well, again, let's look at R2. If we have so if you plot all of these vectors in R2, they actually form a line like this. But that line doesn't go through the origin. And if you take two vectors from this line, so like this maybe, and you add them together, well, you're not going to end up on the line. When you add these vectors, you get this. But this resulting green vector doesn't put you on this line. So that's sort of geometrically speaking why W isn't a subspace. It's because although it is a line, it doesn't go through the origin. There are other ways you can fail to be a subspace. So just for example, in R2 again, suppose we take this collection of vectors. So when I say this collection of vectors, I mean all of the vectors that start at the origin and end somewhere along this curve. So this does contain the origin, so it does contain the 0 vector, but is it closed under addition? Well, let's take this vector. If we add, and another vector in this collection is this vector. If we add these two, do we end up in our collection? Well, no, we end up here, right? That's not in our collection of vectors given by this parabola here. So if you give it a little thought and sort of imagine some different scenarios in R2, what you'll see is that really the only linear subspaces are actually lines through the origin or the entire collection R2. But just to get a little more intuition of what a linear subspace is, let's compare it to span. So suppose we have some vectors in Rn, and we take the span. Then the span of those vectors actually is a subspace. So remember, the span, just by definition, let's prove this. The span by definition is just the collection of all linear combinations of these vectors. So a1, v1 up through a k, vk, where all of these a's are scalars. They're all real numbers. So first of all, to check if this, so let's call this capital V, this span, to check that capital V is a subspace, first of all, 0 has to be, the 0 vector has to be in capital V. So is that the case? Well, yes, because we can choose a1 to be 0 and a2 to be 0 and so on, ak to be 0. And then what does this formula produce? Well, if you choose all zeros for your coefficients a, this formula just produces the 0 vector. And so the 0 vector is in this span, capital V. All right, so now let's check if we start with two vectors in capital V, is it true that the sum is in capital V? So if we take two vectors in a span, is their sum in the same span? Well, if little v is in the span, then that means little v, we can write it as b1, v1 plus and so on up to bk, vk. And we can do the same thing with w. So w, we have to, since it's in this span of the little v's, we have to be able to write it as c1, v1 plus dot, dot, dot up to ck, vk. But then what's the sum? Little v plus little w is the sum of all these, but notice that there are two terms that have the vector v1, so we could actually combine those two terms by factoring out the v1, and that the resulting coefficient is b1 plus c1. And you can see this is going to happen for every term. Up to the last term, there are two vk terms, and the resulting coefficient is bk plus ck. But look, this actually displays v plus w as a linear combination of the v's, right? Here are the coefficients that you need on the v's to produce v plus k, or v plus w. So v plus w is in the span of the v's. Good, that means that this span is closed under addition. So now we have to check scalar multiplication. So if we have a vector little v in this span, capital V, and we choose any old scalar, is the scalar product, r times little v, in the span, capital V? Well, let's check. Little v has to be, we have to be able to write it as b1, v1 plus and so on up to bk, vk, because v is in the span, so it has to be a linear combination of these vectors. So r times little v is r b1 v1 plus so on up to r b k vk. Here I've just distributed the r to each term here. But that's r b1 times the vector v1 plus and so on up to rbk times the vector vk. But this is a linear combination of the vk's, right? The coefficients that display it as a linear combination are rb1 up to rbk. So this is a linear combination of v. So we've checked that this span is also closed under scalar multiplication. So this span, we checked the three properties to be a subspace. So that means that this span is a subspace. All right. So we can, when we picture a subspace, we can actually just picture a span of some vectors, and that will always be a subspace. But actually, it kind of makes sense to ask the question the other way around. We know that a span is a subspace. Is a subspace a span? Well, it turns out that not only is a subspace, not only is every vector space a span, it's actually a span of finitely many vectors, right, if we're starting out in Rn. So let's see why this is the case. So we have a subspace V, and I'm using I'm saying that I'm claiming that V is equal to the span of all of the vectors in V. So first of all, to check if this equals is actually true, let's check that V is contained in its own span. Well, I hope that this is pretty clear, because if we choose little v in capital V, we can write little v as a linear combination of vectors in capital V. Right? V is just 1 times little v, but by definition, that's in the span of V. Right? So every vector in V is in the span of V. All right? Well, now let's check this the other way around. Let's check, is the span of V in capital V? Well, let's take a vector from the span of V. So this would look like some combination of vectors, of finitely many vectors, where all the a's are real numbers and all the v's are in V. But if all the v's are in V, then that means V is a subspace. We're assuming V is a subspace. So that means that V is closed under scalar multiplication. So AK times VK, that's in V. A1 times V1, that's in V, because V is closed under scalar multiplication. All of these terms are in capital V. But then, because V is a subspace, it's closed under addition, and that means that the sum of all of these things is also in V, because V is closed under addition. So we took an arbitrary vector in the span of V, and we showed that it is in V itself. So that means that the span is contained in V. So V is contained in the span is contained in V. That means these two sets have to actually be equal. So V is equal to its own span. All right, so before we showed that every span is a subspace. Now we know that every subspace is a span. So when we picture a subspace, we can actually just picture the span of some vectors, because that's guaranteed to be a subspace, and every subspace is just a span. But notice that I actually claimed something stronger here. I said that if V is in Rn, then V is actually the span of finitely many vectors, and we can choose these vectors to be linearly independent vectors in V. So that's actually a much stronger statement. So let's see how we can do that. Well, first let's choose, I guess, first, if V is just the zero vector, then we're done. There's really nothing to do if V is just the zero vector. So let's suppose that V is not just the zero vector, right? The subspace that consists of only the zero vector, that counts as a subspace. But there's really nothing to show here. You don't need any vectors to create the span if you have only the zero vector. So let's suppose that V is not just the zero vector. Then we can choose some vector V1 in V that isn't the zero vector. Okay, now we have this collection of vectors that has only V1 in it. This is guaranteed to be linearly independent because it has only one vector in it, only one non-zero vector in it. So now let's check, is span of our single vector here all of V? It's definitely contained in V, but is it all of V? Well, it may be. If so, then we're done, because we have a linearly independent collection of vectors that span capital V. But if not, then that means that there is some vector, let's call it v2, in V that is not in span of V, just V1, right? Because the span of V1 is contained in V, but if it's not all of V, then there must be some other vector in V. All right. So now we have a collection of two vectors, V1 and V2. So we need to know, is this linearly independent? Well, it definitely is linearly independent because we've proved before that if you start with a linearly independent set and you throw in a vector not in the span of your originally linear independent set, the resulting set is linearly independent. And that's exactly what we did here, right? We started with a linearly independent set, just V1. We picked one more vector, V2, that isn't in the span of it, and added into our collection of linearly independent vectors. We get another collection that's linearly independent. All right, so now we have this bigger collection that's linearly independent. So we can ask again, is the span of this collection, V1 and V2, is that all of V? If so, then we're done, because we have a linearly independent set of collection, a linearly independent collection in V that spans V. If not, then we can do this whole thing again. Just pick another vector that's not in the span of these two, call it V3, and then add that to our collection of vectors. So now we have V1, V2, V3. Is this resulting collection linearly independent? Well, it is, because we started with a linearly independent collection. We threw in a vector that is not in the span of that collection, and so the result is linearly independent. Okay, you can see that we just need to keep doing this again and again, right? If we, at every step, we just throw in one more vector, check if we've spanned all of V yet. If we haven't, find one more vector to throw in. I guess the only question is, are we sure that this will ever stop? So, all right, it's possible. I mean, at first, it's not clear why you actually ever get to all of V. Well, eventually, this must stop. So if we ever get to V1 up through Vn and then Vn plus 1, so if this process never stopped, we'd eventually get a list of vectors that goes all the way out to Vn plus 1. But remember, we're in Rn, and in Rn, n plus 1 vectors are definitely linearly dependent. That's something that we know from before. So this process, this stepwise process, it always produces linearly independent vectors. But we know if we get to this step of the process, the n plus first step, we would have linearly dependent vectors. But that means that we never actually get this far. So this process of adding more and more vectors, it has to stop before we get to the n plus first step. And that means this stepwise process can only take finitely many steps. So this process, adding vectors one at a time, must terminate with some collection V1 up through Vk, and k has to be less than or equal to n, which is the size of the ambient space that we're in. And just by construction, this collection of vectors is linearly independent. Okay. And also, right, at this terminating point, it has to be that the span of all of these vectors is all of our original vector space V, because we said that this process terminated, but it only terminates if you span the entire space. So when it terminates, we must have actually spanned the entire space. So this stronger version of this statement, we've now proved it. So any subspace is a span, any subspace inside of Rn is a span of finitely many linearly independent vectors. And in fact, we actually proved a little bit more. We proved that the number of vectors has to be less than or equal to n.